31 September 15th. Alright, let's do this. Minimum time difference. Given a list of 24-hour clock points in HHMM format, return the minimum minutes difference between any two time points in the list. Okay. We can convert it into minutes, so we will avoid a lot of conversion. Okay, we'll convert into minutes and we'll sort it, and then we go pairwise. Not pairwise, just like going down. Okay, so that was a strategy. Let's get it going. Alright, so we need to have a int times int. Oh, is that gonna be int? Yeah, definitely gonna be int. Time points dot length size. Okay, and then for int I 0I smaller than time points size I plus plus. We'll have to parse it. I'll probably write a private int parse time points. So I'll pass a time point and I'll return an integer. Okay, so basically we'll get the first two and I'll get the last two. So we'll return time point dot substring. Okay, 0 to 0 2. Right, and now we're gonna do integer dot parse int time point dot this, okay, times 60 plus integer dot parse int time point dot substring 2. Okay, so we don't need this, we don't need this. All we need is times I shall equal to parse time points I arrays dot sort times int rest equal to max dot integer dot maximum, right? And then for int I equal to 1I smaller than time points dot length size I plus plus rest equal to math dot minimum rest times I minus times I minus 1. Now return rest. Huh? Oh, it's a list dot get. My bad. Okay, let's see if this is right. String format error. Oh, my bad. So 3. If it's 0, 1, 2, 3. Yeah, my bad. I forgot there's a colon in the middle. Interesting. Oh, damn. There's a wraparound stuff. Okay, that's fine. So yeah, you can translate that into a minute. 23 hours, 59 minutes is 1439. And 0, 0, we can count that as... can we do something about it? Yes, I think we can. The 2 time points, the difference between the two. Minimum minutes difference, so the total is 1440. So basically it's 1440 minus that, right? So we take the smaller between these two. So it will be, you can say max time point, right? Int. Actually, let's change it over there. So here we can say int max time point should be 24 times 60, right? And now we have this, so int diff shall equal to here. Alright, so we do this, we do this. So that's the difference. And what we need to do here is gonna be either the smallest, the minimum diff, or max time point and minus diff. So the smaller of the two. So that shall be able to solve the wraparound problem. Okay, so let's see. I-39, convert time point into its corresponding minutes. Oh, that is the issue. Because you sort the time, right? You sort the time, that means it's not possible for you to compare the front and end. Yeah, because you do pairwise, 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 and it is possible that... So we just do one more. We'll do one more comparison. As you wrap around, you do one more comparison. Yep. Sort them and perform pairwise diff. Note that time can wrap around. So the difference in minute can be either the can either go T0 to T1 or T1 to T0 with wraparound. So yeah, there's two. So we shall do return max.minimum res, and now we need to wrap around. Right, wrap around. The wrap around will be can we put them in the same? Yes, we can. So we do this +1. Okay, we handle this, and oh, but we sort it. Damn. Okay, that's not possible. So we do that, and now we have a wraparound. Int diff. So we don't have to do this. Diff. Then we wrap around the first, the last to compare with the first time. Alright, so diff shall equal to math dot, no, should be times time points dot size minus 1. Alright, I'm tired of doing time points, so n equal to time points dot size. Okay, so we go, we go time points dot size n. Alright, so basically this minus times 0, so that's a difference, and shift into math dot minimum diff or max time minus diff. Okay, so we handle this wraparound thing. This is over log n. Give this a shot. Should be right. Submit it. Oh, old problem. Done it before. Okay, let's take a look. Solution. Sort. Yes, we get that. Sort it. This and last and first. Oh yeah, we don't have to do the in between. Good point. Because we got this, I got confused about. All right, yeah, I was. My bad. So we basically don't need this. Don't need this. We just need this. So this can come here. So this I can delete. And we can do int. And max time point can also be put in here. It's the same. That's all right. Bucket sort. Now I'm gonna do that. Okay, let's put this one. That count as a solution too. Same as solution 1, but we don't have to perform the wraparound during the pairwise comparison. Only need to do it when comparing times n minus 1 and times 0. Okay, so that's that. Good. All right, let's make something happen. I think we have this one, 2846. I'm actually not sure. 2846. Yep, I have. Oh, I have something already written. Oh, I was trying already. Get path frequency. Oh, I'm already working on it. All right, generate ancestor matrix. I have node, parent, level, graph. I have graph. I put the graph in, but I have a weight as well. Ugh. Okay. And generate ancestor matrix. As ancestor matrix is the levels, so I generate them. Generate ancestor matrix is here, so we have this, and ancestor matrix node $append. This is the current parent. So I go to 1, so we want to go for 1. So on left shift I. If it's small equal to level, it's our ancestor. Current ancestor is ancestor matrix, the node I minus 1, right? It's just its previous, it's I minus 1, 2 to the I minus 1th ancestor, I minus 1th ancestor. I put it in, I plus equal to 1, boom, done. So we handle this. We get its child. We don't want the weight. If it's not this, we'll go for the child, parent, the next level, the graph, ancestor matrix, and levels. Good. This is good. And case I have not done it yet, but I think this one's also done. Generate path frequency. Path frequency. I have a path frequency which has a path frequency t, which is a counter. So I'm doing counter. Path frequency is a list of counters. Okay. And I generate path frequency. Current frequency dot copy. For each node, I have the current frequency. Okay. And then for child weight, if child is not equal to parent, and I will do, yeah, because it's a tree, right? It's a tree, and it doesn't have a back edge, so I can just check to make sure that we don't go through the parent. And the current frequency weight, this weight plus equal 1. Yes, and then we'll go to its child, parent. The graph, we have the path frequency or the current frequency, and towards the end. And then when we're done, okay, yes, I think path frequency is also good. So next, what we need to do is to fill the kth ancestor, right? Oh, the kth ancestor, which is not that easy to do if you think about it. So we can refer back here. We have this kth ancestor. Oh, actually, kth ancestor is not that hard. It's the lowest. So kth ancestor is we basically turn k into yeah. So kth ancestor. Shall we do rest? All right. Okay, so ancestor equal to node itself, and then we have a k, right? And then we need to index equal to 0. Let's start, and we need to shift k to the right. Okay, so we should say while k, and we say if k and 1, right? If k and 1 is equal to 1, then ancestor shall equal to ancestor matrix current ancestors, right? Index. That's basically saying that we are getting the current ancestor. I look great.
Stomach hurts really bad.
Yeah, it's a throat?
Stomach.
Stomach. feel the food is good today? I have some medicine from China, which is for stomach ache. You wanna try?
I don't know.
Well, you can try.
Stomach ache.
Yeah, like if you have diarrhea or stuff.
No, it's not that. It's probably just inflammation. The help with inflammation?
I don't know. Yeah, help with inflammation. Yeah. Really sure.
Say how many?
One. 3 times a day. Put one each time. It is used for intestine inflammation. For example, intestine titus, something like that. So we have ancestor. We just shift its ancestor to a current index, right? And then after that, we can say index plus plus k left shift 1. K shift 1. Keep going, and eventually we can return ancestor, right? It's at the end we just return ancestor. Okay, I'm not 100% sure. Let's take a look at this. Okay, I don't know why I have to switch to KK. You can just make changes. We have ancestors node, index is 0. So while KK is while the K. If this ancestor equal to ancestor matrix, and it's index plus equal 1, KK. Yeah, so that's correct. So the next thing we need to do is def get lowest common ancestor, LCA. Find the lowest common ancestor of the given two nodes. So we can say n1, n2. We definitely need ancestor matrix. Probably it should be fine, right? So if I remember right, we need to know their levels. Yeah, we need to know the levels. You use levels? Yes, levels. Have I ever used levels before? I have. Okay, so levels is going to be a list of integer. Alright. So we basically say if levels, say n1, I want n1 to have a lower level than n2. So if this one is larger than levels n2, we basically swap them. Right, so n1, n2, n2, n1. Right, we swap them. Okay. So once we do that, we have L1, L2, right, equals to level. Now we need to know the ancestor. So n1 is the lower level, n2 is the higher level, which means more down, right? It's more down. So we need to reset n2. Right, and so n2 shall equal to case ancestor. That's what we need. So case self dot case. Oh, forgot self. Right, case ancestor node is going to be n2. Case ancestor shall be levels n2 minus levels n1. Yeah, the case ancestor. I don't know why you want graph. I didn't use graph. Right, I don't use graph. Okay, so now I don't have graph, but I have ancestor mapped. Okay, so n2 reset. Now n1 and n2 are in the same level. Okay, and what's next? Yeah, if they're the same, return it. If n1 is equal to n2, return n1. Right, that's the same. If they're not the same, then we just say while they're not the same. Right. So my idea is while n1 is not equal to n2, then we can. Oh wait, hold on. Level. So level shall equal to levels n1. Okay. So we say while level is larger than 0. Level is the level where they share the same ancestor, right? So I can find their ancestor. I can say a1, a2, right? I can find their ancestor, and then if they're the same, I will reduce the level. If they're not, yeah, like this. So a1, a2 shall equal to self.case ancestor n1 level ancestor matrix self.case ancestor n2 level ancestor matrix, right? If a1 is equal to a2, then level minus equal 1. Else, if these two are not the same, if a1 their ancestor are not the same, which means we shall swap, right? We shall do so basically we say from this going up this much and not gonna work. So we're gonna go from this going up that much. It's if equal to, we'll do this. If it's not equal to, yeah, we swap them first. We say n1, n2, a1, a2, and then level shall equal to, yeah, I forgot about this one. So minimum levels a1, actually levels a2 ancestor minus 1, and then this actually, let's put it here. And we'll return at the end when they get out m1. So now if they're equal, level will be equal. Right, so if we can return, oh wait, the answer is not right. Hold on. If a1 is equal to a2, then O shall be the ancestor. The ancestor is never on the outside, so we have to say n1. right? But at the end, yeah. So it shall be ancestor matrix n1 0. Yeah. Okay. So that's that. That is to get LCA. Okay. So we have this. We generate this. So we generate a frequency path. Okay. Now what we need to find out is for each queries, right? We have 2 for each queries. We get the first one, we get its path frequency, we find its LCA, we get it, and okay, so basically we say res shall equal to 0 times len queries. Actually, why you do this way? Res. Yeah, I don't think it's even necessary to do the other way. Okay, yeah, and then I'll say for source and destination inquiries. Okay, and LCA shall be self dot get LCA source destination ancestor matrix and levels. Ancestor matrix levels. Okay. Now we can say frequency shall equal to path frequency, PF shall equal to path frequency S plus path frequency D minus 2 times path frequency LCA. Okay. Then we need to know the maximum. So I think it does give us. So we'll go Python counter. We go to the documentation, we go to counter. It does say elements most common. What do you give me? The most common. So the most common one. Okay, most common one. Oh, can I just do subtract? I'm actually not sure if I can just do plus and minus on this. Oh, I can. Okay. Alright, so basically, oh my god, rich comparison operations. But there are different stuff. Okay, so multiplication. I didn't really say multiplication. I'm not even sure if I can do multiplication. Wait, hold on, where am I? Oh, what the hell? Okay, so I think I have this. Okay, so we say a equal to counter. I don't know, a equal to 1, b equal no, a equal to 1. Counter should be say a equal to 3, b equal to 1. Okay, a equal to 3, b equal to 1. Can't even see anything. All right. Okay, 2 times a. It is not a times 2. It is not allowed. Okay, now how about let's say b equal to counter, a equal to c equal to 1. No, I think I can just do the same thing. A equal to 4, b equal to 2. How about this? Okay, b is this. Can I say b plus b minus a minus a? Yes. I can do that, which means I cannot do this, but I can do minus twice. Right, path frequency, I can do that. Okay, so now I have path frequency. Then we'll have the most frequent. I say be the most common one. So we get the most common, and I need a sum. So I need a total, right? This is the total edges. So total shall equal to, for v in pf dot values. I forgot. I know items is the values, right? So we have sum. Oh, maybe I can just do. I can just do this. Can I do this? There's sum a dot values. Yes, I can. So basically this minus pf dot most common 1, we do 0 and 1. So that is the answer. Dot append. And I'll return rest. Oof. Yeah, I'll give this a shot. There's so many things that can go wrong. Oh, yeah, I forgot all these part. Okay. Oh, okay. This one's right. Oh, this one's right. Wow, this might be right. Damn. Yeah. Failed. Cannot solve this problem. Cannot solve this problem without going through the hints. Also, it is pretty much impossible to implement the LCA algorithm from scratch without any help. Basically, we produce a path frequency. We DFS the tree from any node and produce a path frequency for each node during DFS. Right. Hold on.
I think it worked.
That fast. Wow, I should tell the father that he had another one. He asked me if I wanted. And I was
Are
like,
you placebo?
I don't care. As long as you feel better, I feel happy.
Maybe don't throw away the Chinese medicine.
Yeah.
You threw away other ones?
No, they are all expired.
Oh.
The one that's left is now expired. This one expires next year.
Oh, is your dad that gave it to you?
No, this is my mom. My dad has another one, and he's asking if I want it. And I told him my mom probably wants it. I think he's still thinking about giving it to me. Yeah. I'm back. I just finished writing this. We DFS the tree from any node and produce a path frequency for each node during DFS. And we can obtain, right, the path from any two. Can get the path, not path frequency. It should be the weight frequency. Yeah, we can obtain the weight frequency from the path between any two nodes by performing source weight frequency plus destination weight frequency minus 2 times LCA weight frequency, where LCA is the lowest common ancestor of source and destination. Then the answer to the source destination pair is the total number of edges minus the most common count of weights. The most difficult part of this algorithm is undoubtedly the LCA. And I need a lot of help to implement the LCA using binary lifting. So path frequency shall be weight frequency, right? So I can say %s, maybe we say path frequency we shall do that to weight frequency. Okay. Alright, let's give this one more shot. And hopefully it will work. Alright, we submit it. Oh! Damn it. Alright, we have an edge case. Index out of range. Huh. Most common. What is the input? One node, right? One node, no edges, and it's to itself. What is the answer? It should be 0, right? Path frequency is, so basically you're saying we have just a counter itself. See the most common. It should be an empty list. Okay, so maybe we can just say, yeah, this is nothing. Path frequency is an empty, right? So the most common is, okay, so we can say is, we put a here, if pf else 0. Let's put this one here, run it. All right, try it again. Oh no. Oh, I was going to say oh no, but yeah, we passed. This is hard. And I think it can be a good interview question, but this is freaking hard. Yeah, Lord. Well, there are other ways to solve this, I'm pretty sure. Prefix sum and LCA on the tree. Binary lifting. Euler tool. Euler tool. Nope. Nope. I probably will go Tarjan. Tarjan's algorithm and lowest common ancestor. Okay. Yep, we'll have to read through this. We might have another way to solve this. You are kidding me. What? It cannot be. Damn. All right, what's the complexity of binary lifting? What's the complexity of this? Binary lifting, O log n. O log n is the binary lifting. N log n to process the tree and then log n for each. N log n to process the tree because you have to go through. You have to go through every single one, right? With your DFS, and as you DFS it, you will do log n. Yes, on log n. Okay, on log n. All right, yeah, it could be the next thing to look at is the Tarjan. We'll probably implement here. So we're still stuck at this problem, but you know, we at least get one of them done. All right.